Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax, and on with the show. Okay, yes, looks like we are on. So, like Jesus said, I'm Steve Strong, a very long time member of F.NSPE, a couple of decades here in Georgia, decades before that in Florida with Florida Engineering Society. I've been a long-time officer as well, I don't know, 20 or so years as an officer in some form or fashion. I've got a lot of years in the industry, especially around communications. I've done power, I've done defense, telemetry for people who remember the old Star Wars program. I did that, so I've been around. I'm now an independent consultant, and so anyway, I was pulled out an old presentation I had done in the past. I don't recall if this group's seen it or not. I know I've done it in some other organizations, but tonight I'm basically going to be talking about free TV and how that can work. Now, we're not talking about some of the free streaming services because those are hit or miss, but if you do have questions about those, I'm happy to explain how the streaming stuff works as well, but this presentation primarily covers the traditional free TV of over-the-air broadcast. But like I say, there's a lot of newer developments with streaming services, but they vary pretty wildly. The technologies are all very similar, but the business practices around free streaming services varies quite a bit. So that's why I'm not in this one. All right, let's see. Make sure everything's still working okay. Yep, audio's good. All right, so some information about some of the standards. You know, the spectrum is regulated, if you will, realistically kind of owned by the federal government. The FCC is in control, so there's lots of standards and things that go along with it, lots of rules and regulations. If you go back in history just a little bit, you'll have the National Television System Committee, NTSC. That's what people think of as your old analog TV. When most of us in this room were kids, you had the rabbit ears and that sort of thing. Maybe you had an off-air antenna on the roof or in the attic or something like that. Yeah, and by the way, I see Lee just grabbed a microphone. There's one over here too. I'm very interactive. For those who haven't seen me do presentations in the past, if you have a question, just feel free to ask, okay? Just give me a minute though, raise your hand, and then I gotta punch a button over here to make sure. You have one already, Lee? Hold on. All right, go ahead.
For the NTSC, do modern TVs still have those tuners, or have they decided to go and not put tuners in with those? Yeah,
so I'm not going to say every single TV manufacturer still has NTSC in it. They're more or less supposed to. There are lots of things the TV manufacturers are supposed to do and they don't do. Which drives us in the industry kind of crazy sometimes. You'll especially see that in the commercial space. So TVs that you might see in a hotel, or now this one's not going to be a commercial TV. This one's just going to be probably a consumer grade TV that they stuck up in here. But stadiums, so for example, at the Braves Stadium, what do they call it? SunTrust, Truist Field now, whatever the current name is. Those are all commercial televisions. I know they were a customer, so I know what TVs they have in there. And they're different tiers, and they have different feature sets. Typically, your commercial TVs and your free-to-guest grade TVs allow a greater level of control remotely. So, for example, the TVs in the Braves Stadium, they can program those remotely. They don't have to go touch every TV. And yes, they have physical remote controls that go with them, but they can keep those hidden away. Most commercial TVs, you can change the channels, do everything you want without ever going to the TV. So that's kind of a long-winded to say they're supposed to have it, but they don't necessarily. I think I have it in here, but I'll address it since you asked anyway now. When you look at well, I know I have the virtual channels, but the kind of the quick answer on that is off-air has a two-part channel, which you've probably seen. You've got a major channel and a minor channel. And the minor channel of 0 is by definition an analog NTSC channel. So most of your TVs that still have that and are doing what they're supposed to do, if you enter 5.0, that means look for the analog channel. Now, that being said, there are basically no analog channels being broadcast anymore. There might be a couple very low power stations that are broadcast NTSC for some very special purposes, but generally speaking, anything that's traditional TV now is all ATSC, what would now be referred to as ATSC 1 or ATSC 3. All right, so good question now. Okay, ATSC, like I just mentioned, is the next generation. That's where we move to what everybody calls digital. The modulation itself is still an analog modulation, but the way that the signal is encoded is a digital data set that's carried over that analog modulation. And that's using 8VSB, which is a derivation of AM, so old AM radio. One of the problems that they had with ATSC, there were two competing standards that went before the government. One of them was 8VSB, and one of them was OFDM, Orthogonal Frequency Division Multiplex, which now finally ATSC 3 is using. OFDM is a much better modulation standard for the purposes of television. As the old saying goes, right tool for the job. And this is no exception. You choose the right type of modulation for what your purposes are. And for off-air television, 8VSB was a horrible choice. But it was the politically connected choice. It was not the technically correct choice. So we've been suffering with that for years. One of the biggest things we suffer with on that is what's called multipath interference, and I'll cover that a little more as well. Also, one of the nice things about ATSC 3 is there's some new technologies that allow for some greater flexibility and some more capabilities in terms of how the television data is carried. So I left my phone over there because I was connecting my computer and my iPad to the internet through my phone. But if you're looking at a phone, you're looking at a video on a phone, 480p resolution, 480 lines of horizontal resolution is more than adequate for a phone. Okay, it's a tiny little thing. You can't really tell. If you're on a 100-inch projection or now LED or LCD TVs, 480 is not going to look very good, so you want higher resolutions. ATSC allows for a nice way to do that, and I'll cover that in some more detail as well. It's also IP-based, so it's very conducive for going back and forth between these different approaches in terms of delivery. It also allows some new features in terms of targeted advertising and that sort of thing. So if you're watching TV, how many of us are sitting there watching some commercial on TV going, I don't care about that. That's got nothing to do with me. I'm not interested in that. Well, they can get better at targeting advertising, so it'll be things that you're interested in. And that's a good thing. It's a good thing for you as a consumer, and it's also a very good thing for the advertisers because they're not wasting money on getting eyeballs that don't care about their product. And yeah, multipath is basically eliminated with that. Yeah, you got a microphone there? Well, that way it's on the recording.
All right. You already know this. Basically, when he's talking about the targeted advertising, I went to a seminar in 2020 up in D.C. where they were touting this, and I brought up the example. This is an excellent example for DC area because you're in 2 states, and for this, DC could be considered a 3rd state. Political advertising. They don't need the TV stations that are doing the targeted advertising. If it's a political race in Maryland, they just tell the TV set to display it only for the Maryland jurisdictions. They can run a separate commercial for political ads in Virginia. Or with a case like a big spread out market like Atlanta, a car dealer here in DeKalb County doesn't need to waste time trying to get customers from Coweta County. That's all I was saying.
Yep.
I was augmenting what you were saying.
Yep, thank you. Yeah, and that's exactly right. And like you said, with politicians, especially congressional districts, they can actually get it down pretty much to the congressional district. So the politicians are only advertising in their district. The other nice thing about it is if you've got Party A, they're going to want to have one ad for people who identify as being associated with Party A. They're going to say, hey, keep voting for me, aren't we great? And then they're going to do a separate ad for people of Party B and say, hey, we know you're really a Party B guy, but here's why you should come switch over to Party A, and it'll be a different ad, right? That way you're not seeing the same ad. So politicians love this stuff, right? So politicians are in control of this stuff. Gee, how do you think this stuff happens? One other nice thing that comes with ATSC 3 is single frequency networks. Those are basically on-channel repeaters. With 8 VSB, doing an on-channel repeater is not impossible, but it's exceedingly expensive and difficult to do, which is why you don't see many of them. But with ATSC 3, that becomes very easy. The theory is that once ATSC 3 is finished being built out with your big high power transmitters in each city, they'll start to put lots of little transmitters all over the city, especially in downtown areas. You look at downtown Atlanta, the Buckhead Financial District, the Perimeter Center, that area, they can actually start to hang a box about yay big on a building, and that will cover the inside of that building essentially, so that you can start to get signal directly onto something like your phone, because your phone has a rotten antenna just because of its size. You can't violate physics there. So yeah.
A place where that would work very well, because I've discussed this with people out there, is the San Francisco Bay Area. Most of the TV stations are on something called Mount Sutro, but there's further in a mountain, what is it? That's not Harvard, no, that's in Los Angeles, but there's another Mount Rudolph or whatever. And one of the major stations in San Francisco area is actually in San Jose, and they can't put their main transmitter on Sutro.
Right.
That's the NBC owned and operated station. So they would be a prime candidate to do the distributed transmission because they have coverage problems to the north in San Francisco. So that, especially in really large markets. Here in Atlanta, we have a few stations licensed to the outer cities, but it's not quite the problem it is in Frisco.
Yeah. But even then, if you look at the Atlanta market, it goes all the way over to Athens, and I think even a little beyond, and it actually covers a few counties in Alabama. So it's a massive physical area. Unlike South Florida, where there's actually 2 market areas in a fraction of the geography of Atlanta. So anyway, let's see, make sure I'm moving the right direction here. Come on. I don't think I missed anything. All right, so the radio. Talked about multipath just a little bit. This is a little bit more detail about what multipath is. So you can imagine if over on the left is your transmitter, you've got your signal going that one straight line directly to the receive antenna, but then you have signal bouncing off of things like office buildings and lakes and water towers. And I had a customer one time years ago that lived kind of south of town, and he was saying, I have this problem. My signal is great all day long, except it starts breaking up in kind of the morning hours and then the evening hours. And I said, give me your address. And I looked it up. Well, right between the transmit towers and his address was Hartsfield Airport. And guess when the planes are really going a lot in and out? It's those 2 times of the day. What I figured out was happening was the airplanes were creating multipath. There were so many airplanes in the sky that it was starting to alter the signal. What that does is you're getting reflected signals. It's the same signal, but it arrives just a little bit later, okay? The way 8VSB works, by receiving 2 signals where they're slightly out of sync from each other, it's destructive interference. With OFDM, you can use some math to actually turn that into constructive interference. So you can actually improve your signal in some ways, all right? So that's what multipath is. Make sure I'm on the right device. Not that device, that device. So one of the things, if any of you guys ever decide to put an off-air antenna at your house to get lots of free channels, by the way, I think I've got just shy of 100 channels at my house right now for free. And depending on which model you plug it into, because I'm down in a hole, it says I shouldn't be getting anything, or maybe I get a half a dozen or something like that. But you know, there are some things you can do to try and help improve that. But one of the things to keep in mind if you do this is there's lots of apps and things out there, lots of different tools to say, well, from where you're standing, your transmit antenna is that way, all right? That's a starting point. That's not where you finish. You'll frequently find that by moving the antenna a little bit one side or the other, you'll actually improve your signal. And it's because of this multipath scenario. What you're doing is you are degrading your primary signal slightly, but you are also degrading one of your interfering signals. And if you can degrade your interfering signal enough outside of the primary receive point of the antenna, you're reducing that more than you're reducing your primary signal, and you improve your signal to noise, all right? Because it's all about how much signal do you have as compared to interfering signals, whether it's interfering like a multipath or just general noise. And I'll show you some of the details about how you want to do this. It's a little bit trickier to do without proper equipment. With proper equipment, it's real simple. I had done this originally to train people who were installers with proper equipment on how to actually go ahead and use their equipment right for an installation. But when I get there, I'll show you guys. You can do it without. Make sure it's on.
Thank you. Just got a new Samsung TV, and it's got gobs of channels coming in. Are we depending on an internet signal that I have there, or are we?
Do you have an antenna?
I don't have it. Didn't connect it.
It looks something like this. It could be a small one. It could be something in your window. Do you have any antenna hooked up to your TV?
I didn't add an antenna to it, but.
Okay, then you're doing some sort of streaming.
Okay.
All right.
Yeah, Steve, the CNR, carrier to noise ratio.
Carrier to noise ratio.
MER is multipath.
Modulation error rate.
Okay.
Yeah. So
Thank you.
thank you. That's a good good point to probably bring that up. Again, I'm used to doing this for people who are already kind of in the know. So carrier to noise is just looking at the power. And I'll show you some spectrum here in just, you know what? Actually, hold that. Let me get to where I have shots of the spectrum, and it'll be easier to show you with a picture. If you're going to do, don't let me forget though, there are some situations where you have TV stations that instead of all kind of being clustered in one area, the transmitters are, you know, like this. You can use multiple antennas in that case and you'll get better performance. But if you're going to, and this is kind of a picture, so if it's a single transmit site, you're going to use one type of antenna. This is the plot that shows you, looks like this is coming off the edge a little bit. Shows you what the antenna pattern looks like, the receive pattern. If you're doing multiple transmit sites and they're close together, then you can still use that one antenna type of scenario. Hold on, I thought I had,
Where'd it go? I somehow lost one of my slides.
But if you're doing, maybe it's in there later, but if you're going to do a situation where your transmitters, like I say, are not close together, like this picture here, you can use multiple antennas. And I know I have stuff on this later. You need to use proper equipment. You don't just go to Home Depot and buy a two-way splitter and run it backwards, because all you're going to do is add to your interference, and you're going to double your noise floor essentially. Because what you're doing is you're adding all that energy together, so your noise, your ambient noise, atmospheric noise, everything else is going to add together, and you're going to get essentially twice as much, which is going to degrade your performance as well. All right, so picking an antenna, antennaweb.org is probably the best site for people who are not highly knowledgeable in the field. TV Fool was the best alternative. Now it's rabbit ears. TV Fool wasn't keeping their database up to date. I love the presentation of the information and the data in TV Fool, but what good does it do you if the information's not up to date? So that's why I kind of now recommend rabbit ears. I just didn't get a chance. I wasn't expecting to do this tonight, so I didn't catch that. Over here in the corner, you can kind of just barely see it because of the way I've got the projector set up. There's this color pie chart kind of thing that is used, and AntennaWeb uses that pie chart to tell you which antenna. So rather than getting into a lot of technical details and measurements and predicted measurements and that sort of thing, AntennaWeb will just tell you, if you want to receive this station, you need an antenna that covers this band and this color of the pie chart. And then you go buy your antenna to match that. What you do is you pick the worst. So you can see yellow over here is the least amount of gain for the antenna, and violet is the most amount of gain, so it works around clockwise. What you would want to do is pick whatever your worst case scenario is for whatever channel you care about. There may be channels in your area that you just don't care about. So if, let's just say for example, all the stations you care about are red, and then you got some violets and some blues, but they're stations you're not interested in, then don't buy an antenna that's going to give you blue and violet. Just go for the red and save yourself some money, that type of thing. Okay. I'll show you a picture of this in a minute too, but higher gain is a narrower lobe. I always liken it to, if everybody remembers the old mag lights, I think you can still buy them, where they have the adjustable beam on them. You can go from a floodlight to a spot beam. Antennas are kind of like that. A little different technology, but it's analogous. The antennas like the yellow and the green are going to be more like floodlights. The violet's going to be more like a spotlight, okay? And that's just physics. There's only so much energy there, and the more narrowly focused it is, the more energy you're getting in. It's the same reason in satellite television and satellite communications, they usually use parabolic reflectors, because you're trying to get this big, huge surface area to kind of gather up that energy and focus it to a very narrow point. All right. Filters. Cell phone filters are pretty important. Televez, the company I used to work for, they had filters built into the antenna, which is where they should be. So now here's an example of the pattern of an antenna. So this one's going to be fairly unidirectional. What this is representing is that if you look primarily at that yellow, the energy that it's grabbing, top is 0 degrees, so the front of the antenna. So you can see in this particular case, it's what, about a 30 degree. So you usually measure these things at the 3 dB point, so 3 dB down from the peak. So it's maybe about 40, 45 degrees on that one. So that's total So divide that in two to get on either side of center. You will still receive throughout the rest of that range, but that's kind of your peak point there. You'll also see, and again, without getting too much into the physics, you'll see some of these side lobes and things like that, and the lobe off the back. Again, that's just the physics of the design of the antenna. There's always practical trade-offs of how much money do you want to put into this, how big do you want this to physically be, and how perfect do you want that front lobe to be versus having these side lobes and rear lobes.
Is that just a standard Atmos, or that's not an LR, huh?
No, that's not an LR.
That's the shorter one.
Yeah, yeah. So, and
There's
that's actually wrong. That should have been the Dynova. Somehow I got that mixed up, but that's actually a Dynova. So this one is, you can see a much broader pattern all the way around. So if you're, couple things you can do. One, if you're in very close and you don't need all that extra gain, you can use something like this. The other thing you can do is, remember that picture I showed you where if you have multiple transmitters from different locations, they're not like this, but they're kind of like this. You can use an antenna like this if you're in close enough and you don't need the extra gain to be able to receive those antennas even though they're coming from different directions, because you have strong enough signal coming from here and here versus just right here. So there's a lot of cities. Depending on where you live in Atlanta, that works too. It just depends on where you live. This is an omnidirectional. Typically, you're only going to use an omnidirectional in things like RVs and boats and that sort of thing because of the trade-offs. You're going to get a lot more of that multipath interference with an omnidirectional because you're picking up stuff coming off the back behind you and everything else. So, did you have a question, Jim?
Do you start with the address and look up something in the book?
Yeah, exactly. So you go to that antennaweb.org site that I gave you. You enter in your address, and it'll ask you, AntennaWeb has one little checkbox that says, is the antenna going to be mounted 30 feet or more above the ground? Yes or no. You check the box if it's 30 feet or above. You don't check the box if it's below, and it will run the calculations for you based on that.
Your ground outside the house?
Yes. Yeah, ground level, because it's all terrain-based. It's using topography. Right. Did you have a question? Okay.
So
Yeah.
is one antenna per TV, or will one antenna drive multiple?
No, and I'll show you some distribution later, but no, there's different kinds of amplifiers and different applications, but no, one antenna for your whole house. As a matter of fact, and that kind of brings up a good point, apartment buildings and condos and hotels and things of that nature, the Brave Stadium, that's what's called a MATV, or a master antenna television system. You can literally have just one antenna, and if you design your system right, you can feed thousands of TVs with one antenna. Okay. So, and there are rules that govern that. That's one of the things I don't remember if I have in this one or not. But a lot of times we'll have businesses that were asking questions about, well, but I thought I had to pay the local broadcast affiliate money for every customer I have in my condo or apartment or whatever it happens to be. And the answer is no. Under federal regulation, you do not. And I actually showed them right out of the CFR the rule that says they don't have to. There's certain stipulations that go with it, but the basic answer is no, you don't. Yeah, so this is what I was talking about before with multiple antennas. If your transmitters are far enough apart that you can't get all your transmitters in the lobe of your antenna, whatever antenna that may be, maybe it's because you need more gain, or maybe it's just because they're too far apart. Whatever the reasons are, that's where you get a multiple antenna installation. And this is what I was talking about before. And multiple cities is a common occurrence for that as well. There's a lot of people who live in a more rural environment, and they're kind of in between two market areas. And they can point one antenna one way and one antenna the other way and pick up their stations from two completely different market areas if you do that. You do not want to use just a standard combiner, like I said, because it's just going to add to the noise floor and it's going to increase your multipath interference for sure. But there are combiners and amplifiers that are designed specifically to address that problem. Probably the best one on the market today is one from, again, my former employer Televez, called the Avant. What that does is each antenna goes into its own input, and then you can program which channel you want from which antenna. That way you completely block out any interfering signals that may come from a different antenna. So that's the best way to do that. It's a little bit pricier, but that is the best way to do that.
If you have enough signal to work with, and you have one antenna for, say, high V, 7 to 13, and a UHF, you can get a combiner which is designed to do that.
Yeah, I didn't want to confuse them with bands at that point. Yeah.
Looks like a splitter, but you gotta read the label.
Yep. Yeah, if you hook it up wrong, it's not going to work. Okay, so this is an example, just one of the, this is an older unit, but the idea is you have different antenna inputs, and some of what Bill was talking about here in this particular case is still an amplifier, but this one happens to have 2 UHF inputs and 1 VHF input. So, the Avant that I was talking about, it's fully programmable. All right, so different kind of amplifiers. You have preamps or preamplifiers. What those are designed to do is take the very weak electrical signal, because remember, an antenna is, basically everybody in here should have had at least some basic EM in school. When you take an electromagnetic field and have that magnetic field flip that around, it's easier to say it the other way. If you have a conductor inside of a magnetic field, a current will be induced. Okay, that's what an antenna is doing at its core. You've got a driven element, which is that device that does what I just talked about. You have directors and you have reflectors that help focus the energy. But it all boils down to you're taking that magnetic field and converting it back into electricity. That is a very weak electrical signal. A preamplifier is purpose-built and designed to take that very weak signal and bump it up. Okay? We talked about how you can distribute signal to thousands of TVs. That preamp is not going to do that job for you. That preamp is strictly to take that very weak signal from the antenna and create something that's more suitable for going down the coax into your house, into the apartment building, whatever it happens to be. Ideally, your preamp should be directly connected to the driven element. Again, it's one of those, as far as I know right now, Televez is the only one that actually does that. Even this much coax is going to introduce noise and degrade your signal because of how weak that signal is. So those are things to think about when you're making antenna purchase decisions. All right, so a mast amp. A mast amp can do dual purpose as a preamp depending on the design. But typically what those are for is to amplify that signal up that you got from your preamp a little bit more. And they're especially useful, well, whether you're combining like that one that I just showed you, or you're trying to use it to send the signal down a rather long piece of coax where you're going to lose too much signal through the coax. You're cranking that signal back up again so that it survives the run of the coax. Yeah, this didn't make it. Our projector's not doing. This was supposed to be in red, and off to the side there it says common mistakes. A lot of times people will say, more is better. We're Americans, right? Bigger numbers are better. No. If you don't need a mast amp because you already have enough signal from the preamp to get in to where you need it to go, don't just add one. Every man-made device like that has pros and cons. Yes, you're amplifying the signal, but you're also introducing a little bit of noise, and you're degrading the quality of that signal just a little bit. Not a lot, but a little bit. So if you don't need that extra amplifier, don't put it in. All you're doing is wasting money and making your signal technically a little bit worse. Maybe it's not worse enough to notice, but why spend money to do yourself harm? And the other thing is always check the input and output specifications on any amplifier you use, because they have a range that they work within, and they're always defined based on a number of channels. So if you have more channels than that specification, then you're going to derate the output levels, and that's because amplifiers are defined primarily in two parameters: gain and total output. So your gain is how many dB you're going to amplify the signal, but like with everything, there's only so much energy available, and you cannot exceed that maximum output energy, or you're going to start to degrade the signal again. So, yes.
Are you talking about more channels from that direction, or more channels that you want?
So any amplifier, it's total number of channels that the amplifier is seeing. So however that may present itself, okay? I've had a lot of professionals that don't pay attention to that part, and they end up trying to figure out why it is that their signal is so lousy coming out of the amplifier. It's because they're coming in way too high of a level going. Sometimes it's too little. Most of the times it's because they have too much signal going in, and I kind of liken it to like you're screaming in somebody's ear. Yeah, it's loud, but you can't really understand it, right? So, Bill, go ahead and grab a mic.
Some point, gentlemen in the viewing audience on YouTube, I have done considerable amount of work troubleshooting interference-related problems for a TV station in Richmond, Virginia, which I used to work for. And the problem was that in most cases they were rural, they used amplifiers, and all of a sudden, starting in 2020, a new cell site went up, or new channels were added to the cell site. These are in the UHF TV channels, roughly 40 to 45. And that's what they call band 71, which is the cell stuff that they got because of what's called the 2020 repack, where we gave back 14 TV channels. And what happened is they were all weak signals 40 miles out from Richmond, but all of a sudden, boom, a few blocks away, a half a mile, they light up a tower. Amplifier didn't know any difference. Steve's X products were pretty good, but I had cases where even their quality products couldn't, work miracles within walking distance of the new cell site. It wasn't just 40 miles out. I had a couple cases within 10 miles of the transmitter. But in one case, the guy was 10.5 miles from the transmitter, used a small amplified antenna inside a cubby hole, and the T-Mobile site was within 500 feet of his condo. We reinvented the wheel and got all the channels. And my channel had the highest power in the Richmond market. And when the calls started coming in after these changes were made, we were like, our antenna got higher. We got more power. What's going on here? The phone started ringing after we did our musical channel shuffle in March of 2020, and T-Mobile started switching on their equipment as fast as they could. But it's my professional opinion. The FCC had a little bit, didn't want to tell anybody because they knew there'd be problems. That's what I got to say. Thank you.
Yeah. So basically what Bill's talking about is again, physics. Nothing is perfect. When you design any circuit, there's always that gray area on the edges, on the bounds, right? You design it for doing a particular task within a particular range, and you specify things where when you're way outside the bounds, you also get a very defined behavior. But when you're in that gray area on either edge, it's not a perfect. It's not a step function. You don't go from 100% to 0%. And that's just reality. That's the physics, again, of designing circuitry. All right, distribution amp. This is what was being asked earlier. Distribution amplifiers are used to take the signal either from the preamp or that masked amp, and it's expecting a much higher level of input signal, and it is putting out an even higher level of output usually to then be split many ways. And again, they're designed purposeful for how many ways you're going to split it. You pick the right amp, right tool for the job again. If this is going into a house where you're splitting it maybe 6 or 8, even 10 ways or something like that, use one type of distribution amplifier. If you're splitting it for a resort community with 4,000 drops or something like that, with probably 16,000 TVs or something like that, then that's a very different amplifier. And in that case, you actually use multiple amplifiers in cascade. So back to that right tool for the job. Don't try and use, as an example, a distribution amplifier as a preamp. It's not going to work. They're not designed for that purpose. Same thing, check the input and output levels. If you're doing this in your house, if you've got enough signal coming from the antenna that you can split it, because let's say you're only splitting it a couple different ways, then don't just stick in a distribution amplifier for the same reason. You're introducing noise, you're degrading the signal, and you're wasting money. If you find that you're not getting enough signal to the distant TVs and that sort of thing, then by all means, that's where you add in a distribution amplifier. So that's just an example of a small residential distribution amplifier with multiple outputs. One thing I will tell you, a lot of times you will see this on a distribution amplifier for residential applications. You won't see this in a commercial level of distribution amp. But for residential, basically what's going on here is these 4 outputs on the right are all amplified at the same level. This one right here, you guys I'm sure can't read it from there, but it says TV, and that one is amplified at a much lower level. The theory being that in a lot of cases where these are installed physically inside the house, there's one TV that's going to be relatively short distance from this device. You don't want to have too much signal going to your TV. Again, like I said before, it's like screaming in somebody's ear. It's loud, but they can't understand you. And to that point, these are your typical TV tuner ranges. Your power level is usually minus 25 to plus 10 dBmV, and that's the common measurement used in North America. They use dBUV in most of the rest of the world. You just add 60 to it and you get dBUV. dBmV, so, and this is probably a good point since not everybody in here is electrical, dB or decibel is just simply a ratio. It's some input to some output, A to B, whatever it happens to be. And when you tack on that suffix like dBmV, you're giving it a reference. So it is a ratio referenced from, in this case, millivolts. Now, unfortunately, we made this just a bit more complicated because when you're doing volts, when you're doing scalar, 6 dB in a scalar is double the voltage. In power, because you have volts and current multiplied, 3 dB is a doubling point. Well, for dBmV, even though it's voltage, it's a scalar, what you're really doing is you're saying it's reference to a millivolt on whatever impedance system you're designing for. So in the case of television, it's a 75 ohm system. So you do Ohm's law and you're doing the calculation with that voltage and that impedance, which then turns it into a power, not a scalar. It's not voltage really, even though it's referenced to voltage. It's referenced to voltage on that particular system. So really in this case, 3 dB is a doubling, or negative 3 dB would be a half. Carry to noise, and I think the next slide's where I've got the good pictures. So the typical minimum carry to noise is 17 dB for ATSC1. It's a little higher for ATSC3. I think it's 20, do you remember? I think it's 20 dB.
The problem
Yeah.
with ATSC3 is since they've got the various modes, it's
Yeah.
a moving target.
I'm talking the minimum, and I'll
It is
show what
probably
LDM
there,
is.
because they do have a mode, they do have a few basic modes which are actually more forgiving than ATSC1.
Yeah.
If you want UHD 4K, you're going to be way above 15 dB.
Yep.
or 17 dB.
So this is just a quick little thing about another data point you use when picking an antenna. If you're in an aesthetically sensitive area, a historic district, a homeowners association that's going to give you a lot of grief or what have you, there are antennas that are designed, like this Dynova here up in the corner, that's actually paintable. You can paint it the same color as your house, mount it along the side of your house, and it kind of disappears. It's almost like camouflage. Most people are pretty happy with that, as long as that type of antenna works for what you're trying to do. So just, like I say, one more data point. There's the other slide I was looking for. I don't know why it ended up down there. Yeah.
Could you just put the antenna in the attic? Hide it?
Yes, yeah. So putting the antenna in the attic, yes. So different antennas can be put in different places. You can put them inside the house, like the old days where you had the rabbit ears on the TV, that kind of thing. You can put them up against a window. You can put them in the attic. The attic is going to perform better than inside the house. If your signal still isn't good enough to put it in the attic, then you need to move outside. So that's kind of your tier, if you will. Inside the house, then the attic, then outside the house. Outside the house is going to be the best possible reception. A lot of places like around the metro area, attic installations are probably just fine. All right. This is what I was telling you before. If you've got two transmitters that are coming from too far away, that's where you use two antennas. The other interesting thing there is, even if these two transmitters are very close in and have very strong signal for your reception, one of the things you'll usually want to do is use what's marketed as a long-range antenna. Because remember, the more you narrow that lobe, the higher the gain. Or the higher the gain, the narrower the lobe, whichever way you want to look at it. Well, in this particular case, if they're kind of roughly 90 degrees apart from each other, even though they may be in close and you don't need the gain of the antenna, what you're looking for is that narrow lobe, so you're rejecting the signal that's coming from over here. That helps get rid of that multipath interference. And I used to have to do that a lot with customers, and I still do it in my consulting business. People come to me and go, well, I don't need that big old high gain antenna because the transmit, I can see it right there. Well, let me tell you, there was one install I helped a customer with years ago in Buckhead. Standing on the roof of the building, it was a tall building with it was like an assisted living facility kind of thing. And you could stand on the roof and you could look right at the transmit antenna. And it was a few miles away, but you know, you're standing high up, a couple hundred feet up on a roof, and a transmit antenna is several hundred feet in the air. You know, it almost felt like you could reach out and touch the thing. But we still had to use very high gain antennas because the building was surrounded by other tall buildings that had highly reflective glass and metal on the outside of the building. So you were getting terrible interference with the signal bouncing off all these other buildings. So by having that high gain antenna, you focus that energy towards the transmitter and cut out a lot of those interfering signals. Again, I stress cut out a lot. It's not perfect. It doesn't mean that you get zero from the side, but you do attenuate it greatly. All right, so here's the pictures I was talking about. Carrier to noise is all you're doing is you're taking the power under this curve as compared to the noise floor here. It says nothing of the actual quality of the signal. It's strictly measuring energy. So you can be fooled because you can have a very high carrier to noise but not a good signal quality. And I'll show you in the next example. Here's an example, and actually let me go back and watch what happens here. Look at your power. Your power there is 22.6. Your carrier to noise is 31.9. Now look at this one. Power is 19.2, but your carrier to noise got better on this one. It's better than 22, right? So, 32, excuse me. Yeah, so 31.9 better than 32.7, right? So the carrier to noise actually improved on this signal. I can tell you, without a doubt, that's a worse signal. Because what you're seeing is here, you're looking for what, when I worked at Motorola, we used to call a Bart's head pattern. By the way, would you turn that microphone off? I see it's still on. Thanks. We used to call it a Bart's head pattern because it looks like Bart Simpson's head, right? Straight side, jaggy hair on top, all right? Kind of looks like Bart Simpson's head. When you look at this one, that's multipath interference you're looking at right there. You are getting extra signals coming in both of these and degrading. This one's going to be worse than this one, all right? But the carrier to noise is actually better. And here's an even more extreme example. Again, look at the carrier to noise. Better than 32.7. That one's 34.8. Okay? That's the worst signal of all of them. That's suffering more from interference than any of the others I just showed you. MER. So MER modulation error rate. I don't think I have a picture in this one. No, I don't. I'll go back. So MER, when you look at the way the signals work in this, I've done another presentation, it's a little more in depth where I show the constellation. The simplest form is if you take a QPSK signal, for example, you've got your normal graph, you've got 4 different quadrants, right? Each one of those quadrants in a quadrature signal has 2 bits represented by each signal. You got 4 signals, hence quad, but each of those symbols represents 2 bits of data, okay? The modulation error rate is that symbol should appear square in the center of that box, if you will. So in that example, you got 4 boxes. Dead center of that box mathematically is where that symbol should appear. How far off of dead center that symbol actually is, as calculated on a vector, so it's not just the scalar, it's actually the vector, that is the modulation error rate. Okay, so a higher number in that case is a better value. Lower number is worse. It means you're farther away from the ideal mathematical symbol. All right. And you can imagine in my example, just where you got that quadrature again, if you have 2 symbols that are right up against each other on that line, you may, as a human, be able to look at it zoomed in and say, oh, this one's clearly in this quadrant and this one's in this quadrant. But to the discriminator, the device that's actually having to decide where that symbol is occurring, it gets real tough for it to pick when it's right on the line like that. Okay, so the channel itself. It's amazing how much confusion there still is on this. FCC off-air channel plan is the RF channel that harkens back to the old NTSC days. This part's more for installers that are used to doing not only off-air but also doing cable systems. The cable systems use the FCC standard plan, which is different. The channel numberings looks the same, but the frequencies are actually different. So they get tripped up by that sometimes. In the US, we use 6 megahertz wide channels. In Europe, they use 8 megahertz wide channels, and the rest of the world, it kind of depends on whose standard they're following, the more European or American. There are 3 different bands for off-air. There's VHF low, which is channels 2 through 6. There's VHF high, which is 7 through 13, and then there's UHF, which is 14 and above. Yeah, okay, so what I was saying here is, so here in town, this was specifically an Atlanta thing that I used as an example. Channel 11 here in Atlanta, which is what the NBC affiliate, is actually RF channel 10. Okay? That one, they just happen to be adjacent. There are others where it's far away. They're not even close. Okay? The reason they did this was when the government was talking about changing the standard, you saw where I talked before about with multipath, it's worse in the lower frequencies, the longer wavelengths. Everybody in NTSC always wanted to be the lowest channel possible because the propagation was better. Trees and things tend to chew up the higher frequencies faster. So everybody wanted to be channel 2. There is no channel 1, different story. Everybody wanted to be channel 2, or at least as close to channel 2 as you can get. And people pay big money for that. With ATSC, now all of a sudden, because of that multipath problem, nobody wants to be channel 2. Everybody wants to be the highest possible channel because the multipath problem is not nearly as bad. Even though the propagation isn't as good, the multipath is worse than the degraded propagation. So when they pulled that on the broadcasters go, oh, wait a minute now. And this is back when channels went, all the way up into the 70s and stuff. Let's look here in town. We got channel 2, we got channel 5, we got channel 11, channel 8, and so on. People know that channel. That's kind of how they think. They just say, oh, what's on channel 5 tonight, right? Well, channel 5 is really on channel 22. Or whatever, I think it's channel 22. 27? Okay, 27.
Unless after the repack they
Yeah, I don't know. I thought, yeah, I could be misremembering, but anyways.
Moved
yeah.
because they were on 39, they couldn't stay there.
Yeah, so anyway, what happens is they're on a different channel. Well, you can imagine the chaos if all these customers, and you go all the way back to some of these people still had the old knob tuners where you had to spin the dial around. By God, I know this is my channel 5. I want to watch my show on channel 5. Well, now all of a sudden it's on channel 22 or 27 or 39 or whatever it happens to be. You're going to confuse the heck out of everybody. And then every time the government sells off more spectrum to the cell phone companies, you got to change it again. Some of these stations have been unfortunate enough, they've had to move a couple of different times. Their customers are going to have fits if they have to try and follow that. So what they ended up doing was they created a virtual channel scheme where channel 5 stays channel 5, channel 2 stays channel 2, regardless of what physical channel it's really on. That way the customers still perceive it as whatever channel they're used to.
Put in mind that you have these big TV stations in big markets like Atlanta. They spend millions of dollars in marketing. So your channel 5, your channel 2, your channel 11. They didn't want to mess with that because they got millions of dollars tied up in stuff like marketing. Did I think that clear enough?
So, yeah, I already covered that. Sorry, I hit something wrong and got out. So I already kind of gave you that verbally. So those are the channel bands. Used to go all the way up to 83. Now we only go up to 36. Channel 37 has always been radio astronomy. So there was always that gap, 37, even when we went up to 83, 37 was never used. Now we stop at 36, 37, still radio astronomy, channel 38 is now cell phone. What's that?
Most of it's sold as cell phone.
Yeah, everything basically above that is cell phone. There's a few exceptions for public safety, but it's pretty much all cell phone. They were the ones with all the money. I talked about the virtualization. So this is just an example of the table. This is in what's called the PSIP, which is the Program and System Information Protocol. This is a whole suite of tables that identifies all the things you need to know so that you can build a map of what's where on the system. That includes things like, where is my video? Where is my English audio? Where is my Spanish audio? Where is my closed caption? All these sorts of things are defined in the PSIP tables. And part of that, and there's even things like event information tables that didn't used to exist under NTSC. You have the EITPF, present and following. So you can say, here's the show that's on right now, and here's the show that's going to come up next. Okay? And there's all these different tables in here. Anyway, one of these sets of tables is a virtual channel table, and that's the one that defines channel 5 is really located over here on this other RF channel. And that way, that's why whenever you get a new TV, you have to scan your channels. It's going through one channel at a time going, is there energy there, yes or no? If yes, receive enough of the data to get the PSIP information and build a map of what is there. Done, move on to the next channel. Energy there? No, okay, move on again until you hit another channel with energy, and then build that map again by using these tables. So this is that specific part, the VCT, the virtual channel table. That's what the viewers see. So when you pick up your remote, you're entering in the channel that they want you to enter, regardless of where it really is. TVCT, or terrestrial virtual channel tables, those are two-part channels. In the cable world, there's a 2 and a 1-part type of table, but in off-air, it's always a 2-parter. Okay. The future is now actually on ATSC 3. When I did this, it was still in development, but it's out there now, still being rolled out. It's not mandated. A lot of stations are interested in doing it because of some of those benefits I talked about before, but it's going to take time to fully roll it out. There's a lot of ATSC 3 stations in Atlanta right now because we're a big market. ATSC 3 uses something called layer division multiplexing. I alluded to that before, where you have something like the phone that has a lower resolution demand than a huge TV. What you can do is you can layer the signal such that you can start with that low resolution signal that does not have a lot of demand in terms of signal quality. And that's great for something like a phone with a crappy antenna. Then what you do is, as you work your way up to the bigger TVs, larger screens, projectors, and that sort of thing, you have these layers. And instead of just resending, well, here's my 480p signal, here's my 720p signal, here's my 1080p signal, here's my 2160p signal, and so on, you do it in pieces. You start with your 480, and then you kind of get the difference from 480 to 720, if you will. So that way, that outer layer, that next outer layer, is not a complete rebroadcast of the same signal, but only the difference. But that difference requires better signal quality. Well, what that does for you is, if you got great signal quality, you get the maximum possible resolution. If for whatever reason, atmospheric conditions, your antenna got moved, whatever it happens to be, or you're just in a bad coverage area, then you start working your way down those layers until you get good, solid reception. And that's the reception that you get, or the resolution you get. Yeah, and remember I talked about boats and RVs and that sort of thing, or a phone you're going to be moving around. It's not a fixed location. So. Yeah, I basically talked about the rest of that. Yeah, so that's kind of a picture of what I was describing. So it gets real complicated as to how we actually make this work. There's tons of math, which is part of why this stuff exists in increments. Because in the days of NTSC, you couldn't possibly do this type of stuff. We didn't have, I mean, it would take a room full of gear to even think about trying to accomplish this. Then you get to ATSC 1, and you had the capabilities that you had there that you could fit into a TV of a reasonable size and a reasonable expense. And even the first TVs that came out ATSC, they were thousands of dollars. Now ATSC 3, this type of capability, even in the late 90s when this was being developed, you just couldn't pack this much math into a chip of a reasonable price and size. Okay, your TV would have to be huge and ridiculously expensive. I thought I had a constellation picture in there. So this is what I was talking about. This is your QPSK over here on the left. And then you've got a couple of different constellations in there. You can see as the constellations get greater, higher orders of modulation, those symbols, those dots get closer together, which means now you have to be far more accurate about the placement of those symbols. You start to drift. You know, you can imagine this dot here, if it drifts just a little bit, now it's hard to tell one from the other. Over here, it can move quite a bit, and you can still figure out which one that is. All right. That was it. So, questions? Yes.
Get them out of QPSK.
There.
Behind you, Roger.
Turn it on.
So, I've tried 3 different antennas in my attic. I've moved one to my roof. I have hardwired direct from the antenna down to the one TV where I really care about reception. I've tried it with and without an amplifier. I have stood up there, spun that antenna around all sorts of different directions. I don't have one of the fancy H30. I don't have $1,500 to drop on one.
Of course.
I use the is wife satisfied with the scan results meter. That's a very time-consuming data point to capture because I'm up on the roof and sweating, and I'm waiting on the scan to complete, and then her to do her assay of all the channels and tell me if it's better or worse. 1 or 2, 3 or 4, 5 or 6. I don't know how to get a better result.
Yeah.
So far north.
So there's a couple things. One is you may want to look at a different antenna.
Almost up to Dawsonville.
Okay.
Got a couple of different antennas. I've looked at a couple of the websites for directionality and guidance as to which way I need to be pointing.
Elevation is going to be your friend in that case.
I'm as high as I can go without on my neighbor's house.
The other thing you can do is, so from what I was hearing you say, you don't need to do a scan every time. What you want to do is do a scan and try and get the channels that are most important, and then find what the worst of those are. And then once you got that in where you can see it, even if it's lousy, now what you're doing to get her on the cell phone in the house, you're not having to keep doing a rescan. You just move the antenna a little bit, back away, because we are bags of salt water basically. We are good conductors. We interfere with the antenna signal. So you got to get a few feet back from the antenna and then let her look at it and then say, is that better or worse? And then you come back to the antenna, move it a little bit the other direction or more the same direction, whatever it happens to be, back away. Again, it's tedious. Without proper test equipment, this is the way it's got to be. But you don't have to do a rescan every time, okay? That'll save you a lot of time right there. All right?
Steve?
Yes.
I had a similar issue at my house, and what I found is some of, not all, but some of the earlier converters from ATSC to NTSC actually had a very nice meter on them, and you could see in real time what your signal strength was.
So actually that's a really good point, Lee. You got to be very careful with those things. A lot of TVs have that as well. It's not signal strength, it's not signal quality per se in any reasonable measurement that any engineer would use. It's whatever the TV manufacturer deems is appropriate for their customer base. Who knows what they've used, what data points they're using. It could be pure power. It could be just some perception of what they think a good quality signal is. It could be in who knows what scale. What those are good for, they're not useless, but what they're good for is relative changes, okay? Don't trust that number for anything more than very likely, well, everyone I've ever seen, a bigger number means better, but what does that mean? How much better? Who knows, but you know, bigger is generally gonna be better, all right? But that's what those are good for, all right? Anything else? I know we're kind of short on time. You got a question, or if not, it can wait to talk to them.
Does he have questions?
Yeah, because we're about out of time, so
I
just,
know, but I'll
yeah.
make it quick.
Okay.
I have spent a considerable amount of time in my last broadcast job last year looking at things. I have antennas to try out. I have a spectrum analyzer. I don't have a test receiver, but I have a spectrum analyzer, which would help with antenna aiming. And if I also, for the people who are getting interference after the 20 repack, I have a handful of cheap filters, and I got a $500 custom job that I'm willing to share my expertise on a no-charge basis, because I'm going to use your data points in the paper I'm generating. That's my quid pro quo. I want information to say the problem isn't just in Richmond, Virginia. The problem, one of my clients was 105 miles away from our tower. He was actually in the Washington market, near where I-81 and I-66 meet, a place called Front Row. Even though my boss didn't want me to do it, I said, I'll do it on my own time, because I was grabbing data, because I'm going to write a thesis-like thing, and hopefully I'll be at NAB one of these days giving my presentation.
Oh, there you go.
So, you want to take my address and phone number? Talk to me after we shut
Yeah,
off.
because we got to get, I know they're wanting to shut down, so thank you, everybody. Yeah, very last minute.
Add this to the, to your.
Yeah, this is a new one that I hadn't had before, too. Thank you.
All right.
All right, guys.
Couple of things here. We've got.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.